Hi, back with me Gia Wulandari in Algorithm Strategy class. In this video, we will start talking about a new topic, which is branch and bound. So for branch and bound, we will divide the video into three videos. The first one, I will talk about general description and also job assignment problem. And for the second video, I will talk about knapsack problem with branch and bound strategy. And the last one, we will talk about traveling salesperson problem. Okay, let's get started with general description of branch and bound. So branch and bound is often used to solve optimization problems, that is problems that minimize or maximize an objective function that do not violate a constraint. So branch and bound usually solve a problem in breadth first search like manner. So it is actually similar to backtracking in the sense that we use state space tree to find a solution, and also we prune a node that doesn't lead to a final solution. So we do not continue a node that is not promising. And in the worst case, the complexity depends on the number of nodes that may exist in the state space tree. But backtracking is often used for non-optimization problem, although it still can solve an optimization problem as well, while branch and bound is often used for optimization problem. And while in backtracking, we usually just continue constructing solution from a parent to its child, while in branch and bound, here we need a way to compute a bound of a partial solution, which node will we use to continue the construction of the solution. It depends on the bound. And in backtracking, usually we use DFS approach, depth first search approach, but in branch and bound, we usually use a breadth first search like approach with some modification. And the most popular one is best first search approach. And in this lecture, we will use best first search approach for all case studies. So, the general idea for best first search, like backtracking, branch and bound with best first search, constructs state space tree to find a solution. And to determine whether a partial solution is promising or not, we compute a bound for each partial solution. And like in breadth first search, we consider nodes at one level before we continue to the next level. But here, for best first search, we only need to check the children of the most promising node based on the bound. So for best first search, if you have a root node like this, you will start with all children of the root, right? So after you check all of the children, you then continue to the next generation or the next level by checking all children of each parent in the first level, like this. But in best first search, we after we are done with one level, we search which one gives us a better result, which one gives us a best result. Let's say this one, so we only continue with this node. And a node or partial solution is said to be non-promising if its bound is not better than the best final solution so far. So let's say we already have a final solution where we continue one child like this and we reach a final solution, for example, and every bound we have here that has not been checked further is not better than the final solution. It means that the other promising nodes are becoming non-promising because no one can lead better than the final solution we have so far. And then a node is said to be non-promising as well if it represents a non-feasible solution because it violates the constraint. So for example, let us consider job assignment problem. You should familiar with the problem already. So we have n jobs and also n workers, and here we want to assign one job to one worker such that one worker exactly have one job, and the workers have their own fees to do each job. So the fees are various, depends on the worker and also the job. And the problem, we want to know how can we assign the jobs to the worker such that each job is assigned to exactly one worker and vice versa, and we have the minimum total fee to pay the workers. So like in backtracking, we need to consider how can we construct a state space tree for this problem. So let us consider n jobs and n workers, where let's say Cij represents the fee for worker I to do job j. And the solution for the assignment problems, we can write it as something like this, where x1 is the job that is assigned to the first worker, and x2 is the job that is assigned to the second worker, and so on until xn is the job that is assigned to the nth worker, the last worker. So we can construct the partial solution one by one. So at the first step, we can determine x1, and then for the next step, we can determine x2, and so on. So in the state space tree, level will represent the order of workers we check. Okay, and the children of a parent represents the job option for the workers on that level. Then compute. So for backtracking, we can just know the way to construct a state space tree, but for branch and bound, we also need to know how can we compute a bound for assignment problem, for this problem. So job assignment problem is the problem to minimize the total fee to pay the workers. So it's a minimization problem, so that here we need to compute a lower bound. If it is maximization problem, then we need to compute upper bound. But here it is minimization problem, so we need to compute a lower bound. So let x1 to xn represents a way to assign the job, as we discussed before on the last slide. And if Cij, it should be in the index as well. If Cij represents the fee for worker I to do job j, then the minimum total fee will be like this. So we add the fee for worker 1 to do job xi, worker 2 to do job x2, and so on until worker n to do job xn. If minimum Ci represents the minimum fee for worker I to do any job, which means the minimum value of Ci1, Ci2 until Cin, then F should be not lower than the minimum of C1, C2, and Cn. Okay? But for the partial solution, we can adjust the lower bound with what we have with the solution we have constructed, and also the solution we has not yet determined. Okay, let us go to the example for a better idea. So here let's say we have n workers and also n jobs. Let's say we have job 1, 2, 3, and 4, and worker A, B, C, and D. And this is the matrices to show the fee for each worker and each job. So for branch and bound, the first one, we have the initialization or the root of the tree. By using best first search here, we need to compute the lower bound first. So cost is the cost we already determined up to this point, and LB stands for lower bound, and the lower bound for this point will be 10 because we cannot pay worker A less than 2, let's say, dollars, and for worker B we cannot pay the worker less than 3 because there's no work that has the fee less than 3, and for worker C the lowest fee we can give is 1, and for worker D the lowest fee we can give the worker is 4. So the lower bound will be the sum of them, which is 10. Okay, and for best first search here, we choose a leaf with best lower bound, which is itself because we only have one node here, so we only have one leaf in the tree up until now, so we choose the only node we have there. And then we check all children of the chosen node. So it will have 4 children because the first level is to determine the job that will be given to worker A. So worker A can be given job 1, 2, 3, or 4. So let us check the first option first. So if the worker A is given job 1, then the 9 is locked as a part of the cost. So the cost we have now is 9. So the total fee we have up to this point is 9, and the lower bound become 17. Why is that? Because for worker A, we already know that we will pay the worker $9, and for worker B the minimum we can pay is 3, and for worker C the minimum we can pay is 1, and for worker D the minimum one is 4. So we add 9, 3, 1, and 4 so that we can have 17. And next, for the second option, if the first worker, which is worker A, is given job 2, then the cost will be 2 up to this point, and the lower bound will be 2 plus 3 plus 1 and plus 4. 2 because it is locked for this option, and 3 because it is the lowest one we can give to worker B. It's the same for C, 1, and D, 4. And the next one, if worker A is given the job 3, then 7 must be included in the total fee we have, and then the lowest fee we can give to worker B will be 4. We cannot give 3 here because the third job 3, has already been given or been assigned to worker A. So worker B cannot be assigned job 3. So the next lowest fee for worker B is 4. So here we add 4 to the lower bound. The same goes to worker C, although the lowest one is here 1, which can be obtained if worker C do job 3, but here because worker A has been given job 3, then we cannot choose this. So the lowest one we have is 5. And for worker D, the lowest one we have is 4. So here we add 7, 4, 5, and 4. And the last one we goes the same. Here the cost is 8 up to this point, and then for worker B, the minimum fee we can give is 3. For C, the minimum one is 1, and for D, the minimum one is 6. We cannot give job 4 to D because it has been taken by worker A. Okay, so now we have 4 leaves here. So it is branch and bound using best first search. So we want to find the best leaf we have. And because it is a minimization problem, the best one here means the lowest bound we have up to this point. And the lowest bound we have here is 10. So we choose that partial solution to check the children of the nodes. So the children will be to determine which job will be given to worker B. So worker B, because A already given job 2, then B can be given job 1, 3, or 4. So we do the similar things. For the first option, A is given job 2 and B is given job 1. It means that the cost we have up until now is 8, and job 1 and job 2 has been taken. So C and D cannot be assigned to the 2 jobs. So the only option they have is only 3 and 4. So the lowest cost for C will be 1 and the lowest fee for D will be 4. So the lowest bound is the sum of 2, 6, 1, and 4, which is 13. The same goes to the other options. And again, we choose the a leaf with best lower bound. And here we compare 17, 20, 18, 13, 14, and 16. And this is the winner. So we continue with that node to check all of its children. So the first option is the next worker, which is worker C, is given the job 3, and also the worker C can be given job 4. But actually, this partial solution implicitly leads to the final solution, because if the worker C is given job 3, we do not have any other option for worker D other than job 4. The same with the other option. If worker C is given job 4, then we do not have any other option for job D, which is 3. So this node already give us a final solution. So instead of computing the lower bound, we can just see the cost of the final solution, which is 13 for the first one and also 25 for the second one. So now we have 7 leaves: 1, 2, 3, 4, 5, 6, and 7. Again, we choose the lowest one, but now here we already got the final solution as the lowest one. What does it mean? It means that even if we continue this node to find the final solution, it will not better than 17, than 20, 18, 17, or 14. Which means we cannot have a final solution that is lower than 13. The best final solution we have so far. And this is obviously not the best because it is larger than 13. Okay, so the chosen node represents a final solution, which means that there is no other partial solution can lead to a better solution or lower than 13. So The solution for this problem is worker A, B, C, and D respectively is given the job 2, 1, 3, and 4 so that we obtain the total fee of 13. Okay, that's all for this video. We will continue another example for branch and bound strategy, which is discrete knapsack, in the next video. Thank you for watching and see you on the next video.